Welcome to Geometry and Topology Online. In this video, I will be presenting the solenoid approach to abstract commensurators. This will highlight joint work with Daniel Studenman. In the video description below, you can find links to several relevant papers if this piques your interest. This video is somewhat longer than some of the other videos in Geometry and Topology Online. I hope you use the YouTube chapters to find natural breakpoints if you need to watch it in more than one sitting. We begin with the definition. An abstract commensurator is going to be a generalization of the automorphism group of a group. Recall that an automorphism of a group is an isomorphism phi from the group to itself. To generalize this notion, we introduce a partial automorphism. A partial automorphism of a group is an isomorphism phi from H to K, where H and K are finite-index subgroups in G. These are sometimes called virtual automorphisms. While individual partial automorphisms may not be composable, there is a natural equivalence relation which enables composition and turns the set of partial automorphisms under this equivalence relation into a group. This group is the abstract commensurator. It is the set of partial automorphisms modulo the equivalence relation of agreement on a common finite-index domain. This definition is difficult to get a handle on, so let's first investigate what is the abstract commensurator of a familiar example. The familiar example we will consider is the integers. To compute the abstract commensurator of the integers, we need to investigate the partial isomorphisms. Partial isomorphism is, of course, an isomorphism between finite-index subgroups H and K. For the integers, we know the finite-index subgroups. Every finite-index subgroup of the integers is a set of non-zero multiples of some positive integer. Therefore, phi goes from nz to mz. Moreover, both nz and mz are abstractly cyclic groups. So phi is determined by its action on n. Phi of n is either positive m or negative n. Therefore, a partial isomorphism is nothing more than multiplication by plus or minus m over n. Excellent, we've understood the entirety of the set. How about the equivalence relation? Well, in investigating the partial isomorphisms and identifying them as multiplication by a fraction, we made no requirement that these fractions be reduced. With some additional work, one can work out that this equivalence relation comes out to exactly equality as fractions. As a conclusion, we determine that the abstract commensurator of the integers is nothing other than the group of non-zero rational numbers under multiplication. This computation is great, and it may lead you to think all abstract commensurators are straightforward to investigate. Of course, if that were so, there would be nothing interesting. And so before getting into the topological approach to commensurators, I want to discuss where commensurators come from in group theory. So where do abstract commensurators come from? What motivates our group theoretic interest in them? A core example is they show up in demonstrations of rigidity in group theory and in geometry and topology. The classic motivating case is in the study of lattices in Lie groups. To be specific, let G be a connected semisimple Lie group satisfying some fine print, and suppose that gamma is a lattice in G. That is, gamma is a discrete and finite covolume subgroup. Celebrated rigidity theorems of Mostow, Prasad, and Margulis for lattices in Lie groups imply that the abstract commensurator of any lattice is in fact a subgroup of the automorphism group of G. That is, the abstract commensurator, that is, the lattice has no symmetries except for those symmetries allowed by the symmetries of the ambient Lie group. Of course, connected semisimple Lie groups themselves are quite rigid objects, with most finite index of their automorphisms being inner. In this case, we might be interested in the intersection of the abstract commensurator with the inner automorphism group which in this setting goes by another name known as the relative commensurator of a subgroup. I won't state the definition. In this setting, Borel makes a much sharper determination of the relative commensurator, which again is going to be the abstract commensurator up to finite index, under an additional assumption on gamma. Namely, if gamma is an arithmetic lattice, then Borel's work implies that the relative commensurator of gamma in G is the rational points of G. This can be thought of as a vast generalization of our motivating example, where we think of the integers as sitting inside the Lie group, the real numbers. Of course, it's not a perfect statement because of my fine print, but it is in the same flavor. Arithmetic lattices are broadly studied. A precise definition would take us too far afield. I'll just say that classic examples of taking the integer points of any rationally defined algebraic group covers most of the spirit of it. In the setting of arithmetic lattices, Margulis's arithmeticity theorem allows us to, in combination with the work of Borel and rigidity, get a purely group-theoretic characterization of arithmeticity. A lattice in a connected semisimple Lie group, satisfying the fine print, is arithmetic if and only if it is infinite index in its abstract commensurator. And this is really something quite incredible. It tells us that the abstract commensurator, this purely group-theoretically defined object entirely in terms of partial isomorphisms of the group, captures deep number-theoretic information about the nature of the lattice and how it sits inside its ambient Lie group. These results on lattices and Lie groups are the starting point for a much longer story about the relationship between commensuration and rigidity. Before moving on from them, I want to mention one more result due to Farb, which connects to the quasi-isometric rigidity of lattices and Lie groups. In many cases, the abstract commensurator of a lattice, arithmetic or not, is isomorphic to its quasi-isometry group. And further investigations continue this thread, understanding the relationship between abstract commensurators, quasi-isometry, and questions of quasi-isometric rigidity. But to keep the discussion focused on concrete examples, I want to turn to two families of groups that are close parallels to arithmetic or linear groups. The mapping class groups of closed finite genus surfaces, and the outer automorphism groups of finite rank free groups. Both of these settings demonstrate a lot of rigidity. This was first seen in the work of Ivanov, justifying several theorems that motivate his meta-conjecture. So Ivanov's meta-conjecture is that any sufficiently rich structure associated to a surface should have as its automorphism group the mapping class group of a surface. And he gives many examples. His work on the automorphism group of the curve complex is one such instance. Motivated by the meta-conjecture, as well as the parallels with linear groups, one might hope to be able to understand the abstract commensurator of a mapping class group of a surface of finite type. And indeed, Ivanov did so. And so for genus at least 2 and any number of punctures, Ivanov proved that the extended mapping class group of a surface of genus G with n punctures has, as its abstract commensurator, itself. There are no hidden commensurations of the mapping class group. Every commensuration of the mapping class group is in fact just conjugation by a mapping class. You do have to allow the orientation reversing ones, but that's the only deviation from the standard mapping class group. The outer automorphism groups of free groups are studied by analogy with mapping class groups of surface groups, and motivated by that analogy, Horbez and Wade found a similar result. With n greater than or equal to 3, the outer automorphism group of a free group of rank n has as its abstract commensurator itself. There are no surprise commensurations, no hidden symmetries of the outer automorphism group of a free group of rank n when n is greater than or equal to 3. You might have noticed that throughout this discussion, the low complexity cases were excluded. In discussing lattices and connected semi-simple Lie groups, we left out PSL2R. Ivanov's theorem requires that the genus of the surface be at least 2. Horbet and Wade's theorem requires that the rank of the free group be at least 3. And so, what obstacle, or is there an obstacle, in these low complexity cases? What's going on with them? Well, the answer is really the same thing as going on with all of them. What's going on with them is that the mapping class group of a surface of genus 1 is isomorphic to the outer automorphism group of a free group of rank 2, is isomorphic to GL2Z, which means that this group is intimately related to PSL2Z, the quintessential lattice sitting inside PSL2R. So, whatever it's going to take to understand the abstract commensurator of these groups boils down to the place exactly where Margulis's arithmeticity theorem does not apply. And in fact, it's well known that any lattice in PSL2R is up to finite index a finite rank free group or the fundamental group of a surface, of a closed surface. And so throughout all of this motivating discussion, we are really interested in what are the abstract commensurators of some of the core basic example groups in group theory. And let's take a look. We saw earlier the abstract commensurator of the integers. It would be nice if we could continue that reasoning and understand, well, it's not a lattice in a connected semi-simple Lie group with trivial center, understand the integer lattice sitting inside the Lie group R to the n. The abstract commensurator of a finite rank free group and the abstract commensurator of the fundamental group of a closed surface are core objects to understand the lattices inside PSL2R. Well, from our opening example, we can understand the abstract commensurator of z to the n. The finite index subgroups of z to the n are well understood. They're assorted finite index lattices, and isomorphisms between them can be understood as appropriate matrices sending the generators of one to a generating set for the other. Chasing it all through using a similar sort of reasoning, you realize that the abstract commensurator of z to the n is rational matrices. It's not too hard. It's a lovely exercise to do. If you want to engage with this talk, pause the video and take a moment to work out the details for yourself. The story is radically different for finite rank free groups and fundamental groups of closed surfaces. Both of them don't actually give us an infinite family of abstract commensurators, because for r greater than or equal to 2, the free group of rank r is finite index in the free group of rank 2. The definition of the abstract commensurator doesn't care about finite index. If you take a finite index subgroup of a group, all of the partial isomorphisms can be restricted to that finite index subgroup, and we see that the abstract commensurator is the same. And so for any finite rank free group, the abstract commensurator of that finite rank free group is isomorphic to the abstract commensurator of the free group of rank 2. There's really only one free commensurator. Similarly, for G at least 2, the fundamental group of a closed surface of genus G is finite index in the fundamental group of a closed surface of genus 2. And so the abstract commensurator of the fundamental group of a surface of genus G is isomorphic to the abstract commensurator of the fundamental group of a surface of genus 2. Just like for the free group, there is really only one surface commensurator. And so we'd very much would like to understand these two groups, but they remain mysterious. They're really not well understood groups at this point in time, and unlike in the case of lattices and higher rank Lie groups, because Margulis's theorem doesn't apply in the PSL2R setting, there's not much to get a handhold on to understand these two groups in particular. And so some other approach, some different point of view is needed. To find this alternative perspective, let's use some topology. To do that, let's motivate our investigation by looking at a topological model of the automorphism group of a group. This starts, of course, with a topological model of the group itself. And for this, we have the well-known Eilenberg-MacLane space of a group. Well, it's only a homotopy type, but that's good enough. A KG1 is a spherical CW complex whose fundamental group is the group that we're interested in. Whitehead's theorem tells us that we can use this space to understand the automorphism group of our group topologically. For our group, the outer automorphism group of that group is isomorphic to the group of homotopy equivalences of a KG1. If we wish to understand the automorphisms, and not outer automorphisms, we simply have to track base points. This perspective is one that seems very fruitful to try and generalize to commensurators, particularly if we're trying to understand the commensurator of a free group or the commensurator of a surface group. Why? Well, for a free group, a graph is a very good KG1, and looking at the homotopy equivalences of a graph has been an incredibly fruitful point of view to understand the outer automorphism group of a free group. Similarly, and older, for a surface of genus G, the Dane-Nielsen-Baer theorem tells us that this perspective on the outer automorphisms of the automorphisms of the fundamental group of a surface goes even further, because the Dane-Nielsen-Baer theorem tells us that any homotopy equivalence of a closed surface is homotopic to a homeomorphism, and therefore the outer automorphism group of the surface group is the mapping class group. Motivated by the success of these models in the cases that we're interested in, as well as the general theory and the general Whitehead theorem, we're curious, is there a similar model of the abstract commensurator of a group? Well, the abstract commensurator requires us to understand all finite-index subgroups. By the usual covering space theory, this is equivalent to understanding all of the finite-sheeted covers all at once. And so, we want a single object that packages all of that information. Here it is. We call it the full solenoid over a space. And so let X be appointed. You can make this go with weaker finiteness assumptions, but it gets more challenging. We need some finiteness just to get a handle on the wide range of possible covers and to make sure that this limit object, whatever it is, doesn't leave a nice category. So what is the full solenoid over a pointed finite spherical complex? Well, it is the inverse limit of the inverse system of finite covers of the space. Simple, right? Just like with the definition of the abstract commensurator, this definition is somewhat tricky to work with, at least at first blush. And so, before diving into some of the consequences, let's revisit our familiar example. Our familiar example was the integers, and a perfectly good, familiar, canonical KG1 for the integers is a circle, given here with its standard cell structure consisting of a single vertex, which we'll think of as the base point, and a single one cell going around that circle. Well, to understand the full solenoid, I need to understand not just the circle, but all of its finite-sheeted covers. It has 2 degree 2 covers. I'm not going to worry about keeping track of the separate pointed covers. It has a degree 2 cover, a degree 3 cover, a degree 4 cover, which factors through the degree 2 cover, a degree 5 cover, not pictured in this diagram, a degree 6 cover, which factors through the degree 2 and degree 3 cover, and so on. You know this lattice, it's familiar. It is the inverse system of natural numbers ordered by divisibility. And we want to understand the inverse limit of this entire topological space. Formally, you can build the inverse limit of a system of topological spaces by taking their product over the entire system and looking at the subset that is compatible with all of the downward arrows. From this point of view, we can get a view on what is a point on the full solenoid over the circle. It's some coherent choice of points in all of the covers. And so if I wanted to illustrate a single point in this full solenoid, I would need to specify for you a choice of point going up through the system of covers. Here's one in red. I've chosen the base point down at the bottom. In the degree 2 cover, I've chosen not the base point, but the other copy of the base point. The degree 4 cover goes up correspondingly. In the degree 3 cover, I've chosen the base point itself, which means that I need to choose a point in the degree 6 cover that is compatible. That's going to be not the first translate away from the base point, but the third, something which is an odd number but divisible by 3. Shifting our perspective and thinking about how could I encode all of this information, well, at the degree 2 cover, I've chosen an element of z mod 2z. At the degree 3 cover, I've chosen an element of z mod 3z. At the degree 4 cover, I've chosen an element of z mod 4z, such that the quotient map from z mod 4z to z mod 2z gives me the same element as my choice in z mod 2z. Similarly, for my integer in z mod 6z. And so a point in S1 hat in the full solenoid over the circle that lies over a given fixed point in the base space is picked out by an element of the profinite completion of the integers. That is incredibly cool. That is an incredibly deep connection. And in fact, this phenomenon, this connection between the profinite completion of the fundamental group and points in the solenoid is quite general. So take a moment, maybe pause the video, draw out a bit more of this lattice, write down a few more points, and then continue, and I'll discuss some of the general facts about the structure of these full solenoids. In the 70s, McCord, motivated from the circle solenoid as it appeared in dynamics, conducted a systematic study of these objects. And in his study, he discovered a lot about the structure of these solenoids. So one, generalizing the fact that we observed in the circle setting, the full solenoid over a space X is in fact a Cantor set bundle over X, and it's not just any Cantor set. The fiber of this bundle is naturally the profinite completion of the fundamental group of X. This follows just from the general structure of the inverse limit. The universal cover maps to every term of the inverse limit because those are finite-sheeted covers, and thus by the universal property of inverse limits, there is a map from the universal cover into the full solenoid. And this map is a leaf of the fibration. It's transverse to the fibers. And even better, we can understand how the image meets a fiber looking back at the circle, and I hope if you're watching this video, you've pulled up a screenshot. If you follow going around the circle once, this changes your choice of element in every point by acting on the chosen element of the profinite completion of the integers by adding 1. So it's in the same coset of the fundamental group. These objects have incredibly rich structure. There's much more to learn about them. They're super cool. But why do we care about them? Well, the full solenoid is going to be the object which furnishes the topological model of the abstract commensurator. The appearance of the profinite completion should clue you in. We're going to have an additional restriction on the groups for which this works. We are going to be limited to understanding groups where the profinite completion sees everything, that is, residually finite groups. So, solenoids is a model of the commensurator. I said the claim out loud, but let's see the theorem. So, working with Daniel Studeman, we proved if you take a finite aspherical CW complex with residually finite fundamental group, or in other words, a finite KG1 for a residually finite group of type F, then the abstract commensurator of your group is isomorphic to the pointed homotopy equivalences of the full solenoid over the space. And you might think, oh, this doesn't actually help. The definition of the abstract commensurator was difficult to get a handle on, and okay, great, you have a topological model, but these solenoids also seem difficult to get a handle on. But the key tool, one of the key tools in our proof is an improvement lemma, and this key tool allows us to get a handle on commensurations in a way that is both local, in the sense that we can look at a specific commensuration, and global in a way that lets us compose them without mucking about with shifting finite covers and picking a finite cover at the same time and all of that business. So the key lemma is if you take a pointed homotopy equivalence of your full solenoid, this pointed homotopy equivalence came from somewhere. In particular, there are finite covers of your base space and a pointed homotopy equivalence between those finite covers, such that as you lift that up the corresponding tower of covers, the resulting induced homotopy equivalence of the solenoid is homotopic to F. What on earth? Think about the surface case. In the surface case, the Dane-Nielsen-Baer theorem is available, and that tells you that every homotopy equivalence, pointed homotopy equivalence of a surface solenoid is homotopic to one which is a limit of homeomorphisms. This is part of a general phenomenon that in work in progress with Mark Pingator, I hope to use to compute many abstract commensurators of groups, many of which we already know the computation, but using this unified proof framework. To conclude, I'd like to discuss some open questions around abstract commensurators that are connected to the solenoid point of view on them, and that I believe this solenoid model will allow an answer to. The first one is about the abstract commensurator, the fundamental group of a closed surface. So Auden showed that the abstract commensurator of the fundamental group of a closed surface is in fact the mapping class group of the solenoid over the surface, so the homeomorphisms mod isotopy. The discussion that I mentioned on the previous slide doesn't quite recover Auden's result because of a subtle difference between homotopy and isotopy, which I hope to resolve, but again, that's part of work in progress. Coming back to the open question, in the work of Biswas, Nog, and Sullivan, as well as work of Auden, there's a connection between the abstract commensurator of the fundamental group of a surface and a so-called Teichmuller space of hyperbolic solenoids. If you're familiar with Teichmuller theory, this is a deformation space of all of the different choices of hyperbolic metric, and this turns out to be dense in the Teichmuller space of a disk, which is Baer's universal Teichmuller space. It's a very rich theory. An open question that I find very interesting is there a good moduli theory of solenoids in general? So in the study of outer automorphism groups of free groups, there's a moduli space of graphs which plays an analogous role to the Teichmuller space. This perspective has been generalized further to studying deformation spaces of group actions on trees. Is there an analog in the solenoid world? For the abstract commensurator of a free group, stay tuned, watch the archive, email me if you want to get updates. In current work in progress with Daniel Studenmund, we've got something coming, but it's not ready for the limelight quite yet. A second open question that I'd like to discuss is the dynamics of the abstract commensurator as it sits inside the homeomorphism group of the boundary. So also in work in preparation with Daniel Studenmund, the abstract commensurator of a free group turns out acts naturally on the boundary of that free group, and even more, we can show that it sits densely inside the homeomorphism group of the boundary of the free group, and that every element acts minimally. That is, it has a dense set of fixed points. really interesting, strange dynamics. In general, if G is a delta hyperbolic group, Daniel and I showed that the abstract commensurator is isomorphic to the relative commensurator of the group sitting inside the homeomorphisms of its Gromov boundary. I think a really interesting question is, when is this inclusion dense for which groups? And what are the dynamics of the elements? To what extent do they follow this free group picture or do something different? Don't really know. We can keep pushing this further. If G is not delta hyperbolic, but it has a good boundary theory, how much of this can be generalized? How does the commensurator relate to this other good boundary theory? Again, very interesting direction for further study. And finally, I want to conclude with an algebraic open question that I think solenoids can help answer. The abstract commensurator, as we saw in examples of z to the n, is GL in Q. GL in Q is virtually simple modulo its center. That is, PSL in Q is simple. And so, for which groups G is the abstract commensurator? Virtually simple modulo its center. And looking specifically at the abstract commensurator of a free group, is this simple? This is a question emphasized by Lubotsky. These open questions I think are quite interesting, and I'd be happy to discuss them at the coffee hour or via email. If you're curious, if you want to read the papers with the details, check out the linked literature down below, particularly the survey on abstract commensurators by Daniel Studenman. It has an extensive bibliography that covers the broad literature about these fascinating groups.